Yeah, thank you very much. So today I continue my lecture about non-local operators of the convolution type, and today I present results of our joint paper with Andrei Pyatnitsky, which is called Periodic Homogenization of Non-Local Operators with convolution type terms. So there is this transcription, and there is this. Okay. So we consider the following operator. So I start just with our problem because we discussed all our preliminary problems before, and now I just state our problem. So we consider operator of the following form: d plus 2 ax minus y epsilon. And we consider the periodic part as a product in factorization way. And here is y minus x dy. So we will consider the problem of the following form. And epsilon is small parameter, and we are interested in the behavior of this operator when epsilon tends to 0. Here, for function a, we assume that this function is a function from L1 and L2 log in D. There is no negative function. It is symmetric function. Today we will consider only symmetric case and symmetrizable because this factorization also imply that we can consider operator with symmetric kernel. And okay, and we also, okay, I write that the integral of that it is just some constant a1, and we also assume the existence of the second moment. It is very important condition for us. Sorry. Yeah, and that's all. And about function lambda and mu, we assume that there is functions periodic, and lambda and mu are bounded between two constants, alpha 1 and alpha 2. So yeah, that's all our assumption. And we prove that this operator converges to the operator of the following form. I write here operator here. There is some positive definite matrix. We define this matrix later. I define this operator as L0. So we will consider the corresponding problem also of the following form. And the main theory, what we prove, that for any f from L2, the solution of this problem, the problem 1, converge to the solution of problem 2. So L epsilon minus m minus f minus L0 minus m f tends to 0 when epsilon tends to 0. We consider our problem in L2, so I don't put here, usually I don't use here this notation. But we consider our problem in L2 on the whole space for any dimension d. And when we need fixed, then we consider torus or RD, then we'll discuss this. And in general, I use just this notation. Okay.
I'm very sorry, but what is theta? This matrix theta?
It's a positive definite constant.
We define, it is a matrix with constant coefficients, and we define it later. It is, yeah, of course, this theta.
So it is sort of encoded some averaging of lambda.
It is some kind of effective matrix, yeah.
Not really, that's the point.
It is effective matrix, and of course, this matrix depends on all coefficient of our initial
May I
problem.
interrupt you for a second?
Yeah.
In fact, this form of the product for the kernel, it's just because in this case it's symmetrizable. We can consider more generic kernel, just mu of x and y, x over epsilon, y over epsilon, but then from the very beginning we should assume that it is symmetric. For this particular form, when it is a product, it's some restriction, but in this case, we don't need this assumption that it's symmetric.
Yeah, because
Symmetrizable.
if we consider the L2 with the following weight, then of course this operator will be symmetric operator with respect to L2 eta. And this is a good function, yeah, because it is bounded by, from zero, it is bounded by some constant. So these two spaces are similar. So, and now I explain the plan of my talk today. The plan is the following. First, we introduce special.
M комплексная или...
No, M is positive. M is real and positive. Он не должен лежать на спектре точно.
Yeah, in fact, M is any number except from the negative real axis, any the complement of the negative real.
So, first step, I introduce a special ansatz. We introduce first ansatz for the function from the Schwarz space in a special form, Then we consider L epsilon, action of operator L epsilon on this ansatz. And we consider inside of this decomposition, we use a special decomposition. And first we extract the terms of the order 1 divided on epsilon. There is, of course, it depends on the function U and epsilon. Okay. Then we extract the term of the order epsilon 0. Okay. And the remainder.
WS равняется RANS is equal to...
Just a second. Now I only explain the plan, and I introduce this ansatz a little bit later.
Some expansion.
Just now, let us understand what we do in the following for the following step. So, after this representation, first we prove that the remainder tends to 0. So we prove this one, and here we used this condition. It is very important for us.
Epsilon 0 to the power 0 is just 1?
Yes. Then we consider the equation on this part of our decomposition. So we put that the first term is equal to 0, because we wouldn't like to have a term of the order 1 divided epsilon. And after that, we obtain the equation on the first character, so-called first character. And next, we equal the second term. There is the main term, in fact, of the order 1. And we equal this term to our effective operator. And after that, we obtain, using this procedure, we obtain the representation for the effective matrix, and we prove that this matrix is positive definite.
Во всей этой конструкции, in all this construction, what changes if you replace lambda and mu by 1? What happens if
But in this situation, it is very simple, because we don't, if lambda and mu is equal to 1, then we don't need corrector. We just obtain the effective matrix.
Yeah, but still you can write down the explicit formula for the effective matrix.
Yeah, sure.
It will be just moments of A. In this case, we can show that Qij is the integral of Zi times Zh times or A of Z over the whole space. There is an explicit formula in this case.
And that is 2 by 2 matrix. No.
Theta is a matrix
D times D.
from 1 to D. And the first corrector is a vector. It is a vector. It will be the vector in L2 TD.
So U is a scalar, so it is that kind of sum ups with the derivatives, yes? That's I, that's...
Yeah, you mean that effective operator? Yeah, there is a effective operator is a good operator. Yeah. Okay. Yeah. It can be written as theta aj d dxy dxj. Yeah, exactly. So let us start to realize this plan. So first introduce ansatz. So we consider any function from the Schwarz space and introduce the function w epsilon in the following way. There is u plus x So we consider the following ansatz. As I understand, this plan is common strategy for the homogenization problem. It is one of the common strategy. So for me, it was new, so it was quite interesting, realized in the case of non-local operators.
If you don't mind, may I explain a bit the source of this strategy?
Yeah.
What we do, we say, assume that we already know that there is such a convergence.
Yeah.
And then U epsilon should be close to U0.
Yes.
So we take U0, which is a nice function, because it's a solution. If the right-hand side is nice, Schwarz class, then solution is also Schwarz class. And we try to construct an approximation of U epsilon in terms of the limit function. And that's the source of this ansatz. So our conjecture is that the function U epsilon, for its principal term, of course, should be equal to U0, but on top of it, there should be some extra term.
Yeah, and in fact, what we prove from all this construction, we will prove the main lemma, which is the following. So if we look on the operator L epsilon acting on this ansatz function, then it is exactly a differential operator, the limit operator for the function u. Yeah? V epsilon is ansatz for some function, plus term which is vanishing. And that is the main representation what we obtain from all these constructions. Okay, and now we should make some technical things. So we consider what is L epsilon W epsilon point x. Let us use our representation for the operator L epsilon. First, we have kx minus y epsilon. Maybe I put lambda x epsilon here, mu y epsilon here, and here I have y minus okay, now we made okay, this is not a good idea. So now we made change of variables. X minus y epsilon is equal to z. Then y is equal to x minus epsilon z. Yeah, and we put this y to our expression, to our representation for the operator, and we use the Taylor series. And we use Taylor series in the following way. Maybe I write it here because I'd like to keep it. So x. So we for at point y we have x minus epsilon z, and we write that it is minus z gradient ux and plus epsilon square. And here I use the Taylor formula for the second term in the following way. T, there is z, z1 minus t dt. I think this one. Is it correct? Yes. Just to check that it is correct formula. It is not too very important thing, but it is better to be sure. So yes, no, of course we have the second derivative here. Do we have here? Yes, that's okay. And now I make changes just here, okay, on the desk. So after this variable, so first epsilon in power d goes to our, as Jacobian, it goes to here, to there. Then I have z here, and for this function I have ux minus epsilon z times gradient plus this term. Okay, let it be in this way. For this term, I also have gradient ux minus epsilon z times double gradient ux plus epsilon square, so on. And now we try to collect, yeah, first of all we see that these two terms is vanishing.
First three terms, yeah.
First three terms. I write here the second just now in this term. So I use the following Taylor. No, because I use this Taylor formula. You see there is equal. You can see equal. And I have the remainder in the following term. But of course, we will prove that this remainder is good, and because here we use all remainder in this function. And we should prove, of course, that the norm of this function tends to 0. Okay, so now we have the following. 1 divided on, so you see that the term of the order, of the first order in epsilon now disappears. So we have the first term of the order 1 divided on epsilon, as I promised. And now look carefully, what is the first term of the order 1 divided on epsilon? Let us collect this one. First of all, we have, maybe I use another chalk. So look, where we see epsilon in power 1, yeah, because it is exactly what gives our this term. So we have here, we get here, then we get here, and then we get here, right? Because we know that all reminders have the order epsilon square. So we look only on epsilon, on the first power of epsilon. And what we have eventually? Eventually we have, and yeah, by the way, in all these terms we have gradient of epsilon. Yes? Because, yeah, now we have not this term, but we have sorry, maybe it is important. Maybe I just use the desk and write it here. So x minus epsilon x and plus epsilon square, and now I missed one term, and I missed here, yes, plus epsilon square. Okay. No, there is no. Yeah, it's here. Okay, so what we have for the first term? We also can consider gradient of Ux as a multiplicator. And for the integral, we have the following expression. A of z mu y divided on epsilon. And then we have minus z plus kappa 1 y divided on epsilon minus kappa 1 x divided on epsilon dz. And now I made, okay. In fact, we have here two variables, x and z, right? So I should write here not y divided on epsilon, but I should write here x epsilon minus z everywhere, yeah? Instead of y divided on epsilon, I should write x epsilon minus z. Okay, now we obtain the first term, plus. And next we should put this term to 0, yeah, because we wouldn't like to keep the term of the order 1 divided on epsilon. And you see, in this way we obtain the equation on the first function of the first character kappa epsilon. And here is integral over RD. It is important. Okay, what we have for the second term? Now we should collect all terms of the order epsilon square. And here what I do, I add here epsilon square 1/2 epsilon square, the second derivative of u x plus, and here I write epsilon square of this remainder minus epsilon 1/2 epsilon square on ux. And this term then goes to phi epsilon. Okay, now look on the terms of the order epsilon square. Sorry, it is quite technical things. So we have this term, epsilon square. Then we have this term of epsilon square, yeah, because we have epsilon here and epsilon here. We have this term, epsilon square, and we have this term, epsilon square. Good. So we can write the expression for our function phi 0, yeah? There is again lambda x divided on epsilon. Now we have the second derivative of the function u at point x. You can see that again all this term contain this multiplicator, the second derivative of u everywhere, yeah? And it is local. What is important, then it is local. It is at point x, which is fixed. We don't need to integrate for this coefficient. So what we have now, we have integral again a z mu x divided on epsilon minus z, and what we now we have here, sorry, there is z of course, yeah. We have 1/2 z. So we have matrix here and we have matrix here. So we can consider the scalar product of these two guys. Then we have minus z, z on kappa 1 at point y, yeah? Kappa 1 at point y divided on epsilon.
Again, tensor product. Yeah?
Again tensor product, of course. Then we have plus kappa 2 of function epsilon at point y divided on epsilon, minus, yes, kappa 1 point x epsilon dz. So let us check. Let me check that I don't miss something. The question on there.
There should be also kappa 2 at the point x over epsilon.
Just a second. So we have 1, 2, z, kappa, yes, sure, of course there is kappa 2. Because there is, it came just from our ansatz for the second term of our ansatz. Yes, I think it's correct. Yeah, and now I again rewrite y divided on epsilon in terms of x and epsilon here and here. Okay, great. And plus phi epsilon x. There is a reminder. Great. So our next goal to consider remainder and to prove that the remainder tends, in norm, tends to 0. You can believe me. Okay, maybe.
At the moment.
It is quite technical moment. Okay. By the way, let us look on the situation what we have now here. So you see that here we have some equation on a new function kappa 1, yeah, and we assume that it is periodic function, so that in fact there is equation on the function in L2 on the torus. It is important moment, and you can see that it is the same equation. So we have equation, there is operator, yeah, there is the main operator which act on the function kappa 1. Now, a little bit later, I rewrite this one, and what is important that the same equation, the same operator acts on the function kappa 2. But now the right-hand side of this equation depends on the kappa 1, which we can find on the previous step. Okay, so now look on the remainder very fast, in a very fast way, because yeah, it is very technical things. But what I'd like to explain that in the remainder we have different terms, and for example, let us look on one of these terms, this one. Look what's happened with this integral. So we have the integral of the following, form. I write this because it is better to a z lambda x mu x. So we have epsilon square here, and we have epsilon square here. So we should prove that this integral is small. So we have integration in RD, and we have integration in T of the following difference of two functions minus okay. So there is one of the term of our remainder, yeah, this one. And how to prove that it is really small in norm in L2? You can see that here we have function. U is a function from the Schwarz space. So if we consider, and we consider epsilon is quite small, so the difference between these two functions is small if this shift is not too large. And our idea is to use some threshold for our integration in RD. So we integrate up to some R. So we consider the integration in RD as the integration over Z, which is less than some parameter, some constant R, which depends, of course, on epsilon plus the tail integral over the outside area. And we can choose this threshold dependent on epsilon in such way that here in this area, this norm is small, and then the integration over all in RD for the rest of this function, you see there is a z and z square. Here we use this our condition that this integral converges. So in this integral is small due to this term, because we can estimate the norm of this difference in L2 and show that uniformly in t. T is just a parameter inside of between 0 and 1. This norm is some I couldn't write that it is proportional to epsilon, but in any case it vanishes when epsilon tends to 0. And the second integral is small because this the norm of this difference is just bounded, and again using the convergence of the integral, we saw that the tail of this integral tends to 0. Okay, so for this term, it can be proved in this way, and another terms has the order epsilon. You can see that only one term here has the order epsilon 0 because epsilon square, and all reminders will have order epsilon in power 3. So in fact we have one epsilon, some extra epsilon, and the proof that the remainder tends to 0, it is more easier for the other terms. So let we check that this part we made. We pass through this estimation, and now look on the first term here, and analyze it, and let us introduce the equation on the first character. The time for break? I don't remember when we start. Maybe 20 minutes. Yeah, we started 20. No, we started 20 minutes, then it is.
Okay.
I don't know. Maybe if you'd like, we can just organize break now and then to continue the first character.
It's up to you. It's up to you.
Just new topic, maybe it's as you want.
Maybe I write equation of the first character and analyze the study of this equation. We will do in the next part. The lecture. So we have the following equation. Let me write here in this way. What is A, operator A? It is the following operator. It is integration over RD there is kappa 1.
Mu of psi, I think, minus z.
Yeah. I just, maybe first I write here and then I change variables. Just thank you. And F is integral again. Okay, so now, yes, because I'd like to find my solution. I'd like to find this function kappa 1 as a periodic function. So I make these changes of variables. Now this new variables is a variable on d-dimensional torus. And I also, it will be for me more suitable to use the following changes, the next changes of variables in the following way. I denote xi minus z by a new variable q. It is again variable in Rd. So z is xi minus q. And now I rewrite everything. On the desk it is very simple. In the following way. psi minus q. Here is mu q. Here is mu q psi dq. I can change minus in both parts of this equation, so that is not a problem. Psi minus q mu q, yes, and psi minus q dq. Okay. So there will be operator in the following form, and I consider A as operator in L2 on the torus. By the way, you can see that this function is again function which is periodic. This function also belongs to the function of the torus, and it is bounded function. It is bounded function because again we use here our assumption on A. Using the Cauchy-Schwarz inequality, it is quite easy to see that for any psi, this integral is bounded. So this function is bounded and belongs to L2, and it is periodic. It is quite. Again, we use this structure. You see that in our study, in our analysis, we use this structure that our kernel has the following form: good convolution kernel with good decaying properties, multiply on the periodic function.